Good afternoon, everyone. My name is Colleen Bertoni. I'm a computational scientist at Argonne National Lab in the Performance Engineering Group. You may have heard me give part of the programming model talk earlier. But for this, I'll be presenting an overview of the exascale system Aurora that will be coming to Argonne next year. So first, I'll start with a high-level overview of Aurora. So first, just for the timeline, we expect the hardware to show up this year, and some of it already has been, and for people to be able to get onto the system next year. Yeah, some of the hardware is already on the floor. This is good news. Just for some of the specs, it will have a peak double precision performance of over 2 exaflops, which should make it one of the fastest machines in the world at the time. It will be composed of over 9,000 nodes. The nodes themselves are composed of 2 Sapphire Rapid CPUs and 6 Ponte Vecchio or PVC GPUs. The CPUs will have high bandwidth memory, so much higher bandwidths over CPUs with DDR memory. Each node will also have 8 slingshot NICs. Aurora will be using a slingshot network, which is similar to what you heard about for Polaris, connected in a dragonfly topology. The overall system memory is very large. It's over 10 petabytes, and it will be attached to a 220 petabyte storage system. The storage layer will be using a new file system layer called Deos, and I'll talk about that in a bit. For the software environment, it will include compilers for C, C++, and Fortran, as well as SYCL, DBC++, Openmp offload, Cocos, and Raja. Again, pretty similar to what's available on Polaris. It will also have many of the standard Intel performance and debugging tools, as well as libraries like MKL, but these will have support for the Intel GPUs. And so this is just some pretty pictures. So in the last few months, the cabinets for Aurora have shown up at Argonne and have been installed in our data center. These are some pictures showing that. So not all the compute blades have been added yet, but there's more to come soon. But what we do have now, and the good news is that it's been connected to the facility's power and cooling infrastructure, like hooked up to the water. So once the rest of the compute blades are added, we should be pretty close to being ready to go. Okay, so prior to the arrival of the full Aurora system, we have still been actively working to prepare. So we've done this by deploying and using a number of Aurora testbed systems, which are shown on this slide. These have been extremely useful for application development testing with the Intel software stack, which we'll eventually use that in Aurora. So we sort of started a long time ago, so back in 2019 with testing on the Iris GPUs, which are very low power integrated GPUs from Intel. And until recently, we were mainly using the Arcticus system, which had nodes with the Intel Xe HP GPUs. Those are a precursor to the Ponte Vecchio GPUs, which will be in Aurora. Recently, however, we brought up Florentia system, which has early silicon PVC GPUs, which are fairly similar to those on Aurora. They're not exactly the same, but they're pretty close. So right now, it's a really good opportunity for application developers to test on something pretty similar to what will be on Aurora, and maybe even more importantly, test out the software stack. So you can see us going from 1 GPU per node to 2 GPUs per node to 4 GPUs per node, and finally, with the real PVC, 6 GPUs per node. And then also later this year, we'll be getting Sunspot, which is a test and development system with the actual Aurora hardware and software, just on a smaller scale. So we will be able to test on that. And then next year, the full Aurora system should be start becoming available to users. So a little bit more about PVC, or the compute node. So Aurora is the first large-scale system that will be using the new Intel Ponte Vecchio GPUs. Like I mentioned before, each node will contain 6 of the GPUs, and they'll be connected in an all-to-all fashion. The node also has 2 Sapphire Rapid Xeon CPUs and 8 Slingshot Fabric endpoints. So while Intel GPUs are somewhat new in the HPC market, Intel has been building GPUs for a long time, so starting with their Gen 1 GPUs going back over 10 years. This has evolved over a series of generations, and the most recent generation, Gen 12, has now been rebranded as the Xe GPU line. So this is in accordance with Intel's broader kind of marketing shift and aims in the GPU market. But if you do have a laptop with an Intel processor in it, their chances are pretty high that you probably also have an Intel integrated GPU in it, which is a lower power Intel integrated GPU, maybe a Gen 9 or Gen 10, or sorry, Gen 11. And we've actually used those for a few years to help develop and prepare applications using the Aurora software stack, like I mentioned before. So there's actually a lot of continuity in what Intel has been doing with GPUs. This is more of a scaling up of what Intel has done in the past rather than something completely and totally new. Yes, sorry, I was having some problem with the slides. So, but in line with what they're moving towards, Intel is moving towards, they're offering a number of different GPU products that target different areas of the GPU market. The ones that are currently available and have been in the past are those low power integrated ones that I talked about. So the XELP ones, these are the ones that are in laptops, but in addition to these lower power ones, they also are going to be offering higher power GPUs, so ranging from the XE-HPG, which is for gaming, to the HP line, which is targeted at data centers, and then finally to the XE-HPC, which are the HPC-oriented GPUs that we'll be using on Aurora. So while the capabilities of these different types of GPUs all differ, they're all in a common architectural family. And so just to give people a little bit of a flavor of what that looks like and how it may be similar to the other GPUs, I want to give a brief overview of the main components of the XE line architecture. So I won't go into too much detail, but I wanted to give a high-level overview. So the basic computational unit of an Intel GPU is the vector engine. This used to be called an execution unit. So at some point, Intel changed some of the names. So the old name is in parentheses for this set of slides. So these are very simple cores themselves with things like a register file, separate pipelines for different types of instructions. And in addition to the vector engine, it might also have a matrix engine, which would be kind of similar to a tensor core that's optimized for tensor operations. And then the vector engines are all bundled together into an XE core. This used to be called a subslice. Most GPUs have the same sort of hierarchical organization where you have different pieces of the GPU made by combining other pieces together. So in this case, the XE core is made of bundling a bunch of vector engines together and then sharing some resources in that unit or that level. So here the vector engines and matrix engines in the XE core, these share caches and they share local memory. There's a common load store unit for access to the GPU memory, again, which all the vector engines in this core share. And then the XE cores are all bundled together into an XE slice. So at this level, the XE cores share hardware context, and there are also sometimes things like ray tracing units and a couple of other things. And then one more level up the hierarchy, the slices are bundled together to form a stack, or a tile in the older terminology. All the slices in the stack will share L2 cache, memory controllers to GPU memory, a media engine, and XE link high-speed coherent fabric. That's the GPU to GPU high-speed fabric, kind of like NVLink. And then finally, the full GPU consists of some number of the XE stacks combined together, which are the GPU memory. One of the big distinguishing features of the different Intel GPUs is that the number of slices and stacks can vary. So for instance, the integrated GPUs would have less of those than the HPC GPUs. Okay, so that was just kind of walking through the hierarchy. Then a little more about the Intel Ponte Vecchio GPU. So hopefully we can talk about it more later this year. But right now, a lot of it is still NDA. However, Intel had an architecture day late last year, and they provided an introduction to the PVC GPU with some nicely made slides. So here's showing two of the nicely made slides. They also have a decent amount of information on this link. and also the link that the previous page has had if you grab the One API GPU optimization guide. But there's information there, and in this specific presentation, Intel showed like the components that make up the GPU and the performance. So here they're showing performance numbers for the A0 spin of the PVC. And when I say A0, this means an early silicon version. So we expect these numbers to be improved in the future. That's why there's a greater than in these numbers. But for what they presented, it was greater than 45 single precision floating point performance and greater than 5 terabytes per second memory bandwidth. And again, early silicon, so we expect that to improve in the future. So this is just a summary of what I showed earlier, the hierarchical sort of architecture from XE core to slice to stack to total GPU. So the specific details for PVC that Intel has released is that the XE core is composed of 8 vector engines and 8 matrix engines. It also has 512 kilobyte L1 cache that can be partitioned into either an L1 cache or shared local memory. Then 16 of the XE cores are grouped together to form the XE slice. And then 4 slices are grouped together with a large L2 cache of HBM memory control, 4 HBM memory controllers, which form a stack, and then 1 or more stacks combined on a socket to form the PVC GPU. So that was the Intel GPU, at least what we can talk about for now. Another novel feature that Aurora will have is the file system. So the IO system that we'll be using on Aurora will be called DAOS, which stands for Distributed Asynchronous Object Store. So DAOS will be very large with a total 230 petabyte capacity, and it's fast with over 250 terabytes per second bandwidth. In addition, there are some novel aspects of DAOS where it offers a new storage API, which you can use if you want, but if you don't want to, you can just use it as a regular file system in the way you're used to, just like on Polaris. It has a standard POSIX IO, MPI IO, HDF5. So for most people, this will just look like a large, fast file system. So then I wanted to take a quick look at the overall HPC landscape here in the US and the Department of Energy. So this is just some of the previous systems and the years of delivery. So I just wanted to point out some things. First, all of the new systems or recent and new systems are all heterogeneous CPU plus GPU systems. And then also that the vendors are different, especially from what they used to be. So back in 2018, the 2 big systems, Summit and Sierra, were both IBM with NVIDIA GPUs. And then even like you see in Polaris and with Perlmutter, it's still NVIDIA GPUs. But a lot of the newer systems that are coming in the future will be either AMD or Intel GPUs as well. So we're getting more variety in the GPU market. So like Aurora, Intel GPUs, Frontier, AMD GPUs. So there are a variety of GPU vendors in these systems. And one thing that comes with that is typically they each have their own proprietary software. So this poses a challenge for developers, like how can you write your software to run on all these systems and be portable, assuming you want to run on all of them, when you have different proprietary software on the different ones of them. So with that in mind, let's talk about the software environment on Aurora. The program environment is based on Intel's One API industry specification. This provides a specification for Intel's implementation of a language, so that's DP++ or Data Parallel C++, which I'll talk about in a second. It's based on the SYCL programming model, and also a number of lower level interfaces that Intel thinks should be standard across vendors. So in addition to what's in the One API specification directly, the One API toolkits and products, which you can see here. This includes basically what will be on Aurora. So it's a set of Intel compilers and runtime libraries for languages like C, C++, and Fortran, Openmp 5 plus, Python, and also libraries like MKL, DNN, DAL for machine learning and data science, and then MPI. Plus also Intel's tools for performance analysis, like Advisor, VTune, and Inspector, to help with debugging. And then just to get more specific, this is a list of the programming models which will be available in Aurora. This is a bit more than the ones just from Intel, since we're also supporting some just ECP funded programming models. So in addition to the ones from Intel One API toolchains like SYCL and Openmp, we provide Cocos and Raja. Those are C++ or ECP funded C++ frameworks. We talked about those earlier. They're also supported on Polaris. CUDA is proprietary to NVIDIA, so that won't be available on Aurora. But there is an alternative to CUDA called HIP, which is developed by AMD for AMD and NVIDIA GPUs. And work is underway to add an Intel backend to this so that you can run HIP code on Intel GPUs as well. This is an ECP funded project, so it's pretty much, it's very experimental right now. We're still testing, but we're hoping to get that working. So you can see that a lot of these program models are pretty similar to what is available on Polaris. So to some extent, if you are developing code with one of these models on Polaris, you hopefully will be able to also run it on Aurora. Okay, so let's go through some of the program models in a little more detail. If you heard the previous program model talk, you're probably already familiar with this, but just in case people weren't around, we're going to go through a little bit of detail about each of them. So let's start with data parallel C++ or SYCL. So SYCL, this is a relatively newer programming model. It was announced in 2014 by the Kronos Group. The Kronos Group is the group of people who are responsible for OpenCL as well. So that's been around which has been around for a very long time. And this group is very familiar with heterogeneous computing. SYCL has started seeing more and more adoption in recent years. It's a C++ extension or abstraction layer. So like you can see in the picture, it encompasses all of C++17 with more offloading. It's pretty similar to OpenCL in terms of a lot of the concepts and how it's doing heterogeneous computing. But one big difference is that it's single source. So the code you want to run on the GPU can be in the same file as the code running on the CPU, which is different from OpenCL. So while SYCL is an open standard, and a lot of people have implementations of it, Intel has a specific implementation of SYCL called Data Parallel C++ or DPC++. This is basically SYCL plus some extensions. Actually, a lot of the extensions have been brought into the SYCL specification already, so they're quite similar. But this implementation is from Intel. It's open source on GitHub. It also has the ability to be extended to other other platforms. So this has already been done to support codes running on NVIDIA and AMD GPUs using DPC++ with NVIDIA and AMD backends. And another important program model for Aurora is Openmp. This one we're working closely with Intel to ensure that it's optimized on Aurora. Openmp has been around for a long time, and probably everyone here is already familiar with it. Since version 4.5, it's included the ability to offload code onto GPUs, like you guys saw earlier. This is a really important model since the vendors behind a lot of the new supercomputers like Frontier, Aurora, and Perlmutter are all providing compilers and runtimes for Openmp, so it should be portable across different systems. However, there are varying implementations with slightly different implementations of the standard, so you might see some differences. It's also important since right now this works with Fortran as well as C++, so it's probably maybe the main native option for Fortran to offload right now. And then I also wanted to emphasize that at least, for Intel on Aurora, Intel is very strongly committed to supporting Fortran on Aurora. So the initial implementations of Fortran with Openmp offload support will support up to Fortran 2008 and Openmp 5 for offloading. So Intel, for Aurora, Intel basically re-implemented their Fortran compiler. So they redid a lot of stuff, and right now there's some bug that's kind of in a beta form, but we expect it to be very robust in the near future. And then I mentioned it before, but I just wanted to reiterate that a lot of the standard Intel tools that you've maybe used on CPUs before will also be available on Aurora. So for instance, the performance tools like vTune and Advisor will be available for Aurora to help with optimizing the GPU code. There will also be the kind of standard Intel libraries like 1DNN, or sorry, like MKL, which will be available for Intel GPUs with an optimized version for the Intel GPUs. We actually have a very good collaboration with the MKL team. So if you have a math workload or a code that uses a lot of heavy math that you want to make sure will run on Aurora on the Intel GPUs, please feel free to contact me afterwards and we can see if the functions that you want to offload with MKL will be able to run on the GPU, or if we need to ask Intel to additionally try to implement something. So also there will be AI and analytics libraries like Intel 1DNN and 1DAL, which will be available for use by learning and analytics applications. And then the last thing I wanted to talk about was a few slides just to talk about work being done to prepare applications for Aurora. So Intel has been working with more than 40 projects from the Aurora or Argonne Early Science Program and the Exascale Computing Program to prepare them for Aurora. Many of these projects contain more than one code. So even though it's 40 projects, it's more like working with 50 applications and software packages. This has involved a lot of people at Argonne and Intel and many more external collaborators, and it's been a big effort, and so far we've seen a lot of good progress. And on that, I wanted to point out sort of two showcase applications that showed up in the Hot Chip 34 symposium earlier this year. The results were so good that like Intel wanted to present them. So this is comparing for the NECRS code running on an NVIDIA A100 versus running on the Intel PVC node or PVC GPU. So for instance, for NECRS, if you look at the plot on the right, on average, it's getting about higher is better. So blue is Ponte Vecchio, green is A100. So since higher is better, Ponte Vecchio you could see is larger, and on average it has about a 1.5x performance lead over NVIDIA A100. And then the other showcase that was pointed out at this conference was Openmp, which is an Openmp offload code. Again, higher is better. So showing that running on PVC with this code was about 2x better than running on NVIDIA A100. So and if you have questions about those, we can talk a little bit more, or you can grab this presentation by the reference here. Okay, and that's all I wanted to talk about. So thank you very much for your time.